In this problem, we are told we have a 0.350 molar solution of phosphoric acid. And phosphoric acid is a triprotic acid, meaning that it has 3 acidic protons and therefore undergoes 3 dissociations. And here are the 3 pKa values for those 3 different dissociations. We're asked to estimate the pH and the concentrations of all the species. So to wrap my head around this problem, I'm going to write out the 3 dissociations that occur, and I'm also going to calculate the Ka for each of these dissociations, and I can calculate that based on the pKa. Remember that P is equal to the negative log of anything. So if I have the pKa, that is the negative log of my Ka. So to calculate my Ka, what I do is I take 10 to the minus pKa. So 10 to the minus 2.16, which was my pKa1, is 6.92 times 10 to the minus 3. That is my Ka for the first dissociation of phosphoric acid. Now, I calculated the other 2 values as well, and as we discussed in class, we can see that these Ka values are much greater. This Ka value is much greater than the other 2 dissociations. So all of our hydronium, we're going to assume, comes from the dissociation of phosphoric acid, and a negligible amount that we can just basically ignore is going to be generated from the other 2 dissociations. So since we're asked to estimate the pH, I'm going to look at my first dissociation here using my ICE chart to determine how much hydronium is going to be generated. So here's my initial concentration of phosphoric acid. It's going to shift to the right to establish equilibrium, and my concentration of hydronium and its conjugate base are going to be equal to X. Now, the problem asks me to estimate. My phosphoric acid Ka for my first dissociation is relatively large for a weak acid, so I would not be able to eliminate X here using the 5% rule. I would really have to use the quadratic equation if I wanted to calculate an actual concentration of hydronium. But since it says estimate, I'm going to assume that it's going to allow me to eliminate the X here. It's actually about 14%, so it would not work for the 5% rule. But if I eliminate that X and just multiply both sides by 0.350, I'll get 2.422 times 10 to the minus 3 is equal to X squared. And if I take the square root of both sides, then that will give me X. And so now I have the concentration of hydronium, and of course my pH is going to be the negative log of that value, which is 1.31. So now that I know my concentration of hydronium, 4.92 times 10 to the minus 2, or estimated it, I can estimate my concentration of hydroxide. We know from the relationship of Kw, the concentration of hydroxide times hydronium, is always equal to 1 times 10 to the minus 14th at 25 degrees Celsius. I can just solve for the unknown of hydroxide by dividing my concentration of hydronium into 1 times 10 to the minus 14th. So I get my concentration of hydroxide approximately 2.03 times 10 to the minus 13th. So my concentration of phosphoric acid is going to be approximately 0.350. I could actually subtract my 4.92 times 10 to the minus 2 from this. I'm not sure how much of an estimation Sapliing wants, so if it didn't take this, then I would subtract my 4.92 times 10 to the minus 2 to see if that would give me the answer. And then the conjugate base of phosphoric acid will be equal to the concentration of hydronium, so 4.92 times 10 to the minus 2. So now that I know my concentration of the conjugate base of phosphoric acid, I can look at calculating my concentration of hydrogen phosphate, because that's the conjugate base of this acid. And I've already calculated my Ka2 based on my pKa values, so I'm going to set up an ICE chart. My 4.92 times 10 to the minus 2 is going to be my initial concentration of my dihydrogen phosphate, and then my hydronium concentration is equal to that. So to begin with, I have 0 concentration of my conjugate base. My equilibrium has to shift to the has to shift to the right. Now, X here definitely is going to fall under the 5% rule, so I can eliminate it in my addition and my subtraction. And what happens is my concentration of hydronium and dihydrogen phosphate are the same, so my concentration of dihydrogen phosphate ends up being the same as my Ka. So the concentration of hydrogen phosphate is equal to 6.17 times 10 to the minus 8. So we go back to Sapliing, and let's see. So we've looked at calculating all of these concentrations and the pH. The last concentration we've got to calculate is the phosphate. And I tried to see if Sapliing would take this, but it looks like it's not going to check my answers until everything is entered. I'm not sure I want to take the time to do that. I'm going to let you see what it wants. All right. So let's look at calculating the concentration of phosphate. So this will be our last dissociation. Our monohydrogen phosphate only has one acidic hydrogen. And here is our equilibrium equation. And my initial concentration of my monohydrogen phosphate, I've already calculated 6.17 times 10 to the minus 8. My concentration of hydronium comes from my first dissociation of phosphoric acid, so 4.92 times 10 to the minus 2, and phosphate initially has 0 concentration. So we've got to shift to the right to get to equilibrium, and I didn't even put plus x down here because this x is going to be so small, I know without a doubt that I can eliminate it in my addition and subtraction. So here's my Ka3 value, very, very small. And when I plug in my values for hydronium and monohydrogen phosphate, this is what I get. And then I just rearrange algebraically to solve for x. Here's my Ka value. I'm going to multiply both sides by 6.17 times 10 to the minus 8. Divide both sides by 4.97 times 10 to the minus 2. And when I do that, I get the concentration of phosphate, which is x, is 6.01 times 10 to the minus 21, which is so incredibly tiny. Let me just double check that. Yeah, my original answer didn't quite make sense. Minus 8 plus minus 13 would be negative. When we add these two, that would be minus 21. And minus 21 divided by a power of minus 2 would be a power of minus 19. So 6.01 times 10 to the minus 19 is what I get as my final concentration of phosphate.